In a previous video, we worked with Wolfram Cloud or Mathematica, and we're working building up some intuition about ideas from statistics. And we looked at sort of what's called known as z-scores or confidence intervals. And so in that game, you sort of you have some population, and then you have some samples from the population, and you take the mean of those samples, and then from there you want to try to figure out a range in which you think the mean of the population falls. And so you have this idea of the confidence interval. So you have some number z, which depends on how much confidence you would like to have. So one of the standards is I would like to be 95% sure, and then it's a problem whether it's too big or too small. That's called there are games whether they're one tail or two tail, but so if you want to be 95% sure and you have like a two tail problem, then the z ends up to be a value of 196, and you multiply that 196 by the standard deviation of the population, and divide that by the square root of n. So your region shrinks if you take more samples. That makes sense. And then and we played around with that, and that's in some sense the problem there. The thing that doesn't make sense is the standard deviation, that S in the formula that you're seeing there, is the sample standard deviation, strictly speaking. And that sort of doesn't make sense to say that we know the sample standard deviation, but we don't know its average. Usually the average is easier to figure out than the standard deviation. So what's easier to get then, of course, is the standard deviation or the spread in the sample. So we would like to replace that S, that population standard deviation, with a sample standard deviation. And that means, strictly speaking, moving to what they call the t distribution. So moving to the t distribution is going to change the value of z. Okay, so that's what we want to build up our intuition about. Okay, so that all this is just me saying just that there is this sort of spread around. You take your sample, populate your sample average, and you want to use that to put sort of confidence interval around what you think the mean population, the mean of the population will be, and you have these z values. Okay. And now let's see that there is this thing called a t distribution, that it is different than the normal distribution, and then see its effect on the z, on this 196. Okay. So just sort of build up a little bit slowly. Some individual things I'm going to use. I'm going to have a variable for the number of samples. I'll start off simply with 2. And then I can use this thing called random variate normal distribution. And that will pull 2 independent samples, because my num samples is 2. It'll pull 2 samples from a normal distribution with an average of 0 and a standard deviation of 1. That's the standard normal distribution. And from those, I can calculate the mean and the standard deviation. Okay, so far so good. Okay, now what I'd like to do is get a number of them. So I have J is going to be ultimately what I was calling above the number of samples, but I'm going to vary that. So for a given J, for a given J, say J of 2, I'm going to get 2 samples from my normal distribution, And I'm going to calculate the standard deviation of that and add it to a vector. So I'm doing that 5,000 times. I'm going to get 5,000 runs of getting two samples and figure out um, the sort of the standard deviation over all those 5,000, or sorry, get the mean of those standard deviations, and then go to the next j, then go to j equals 3, j equals 4. And I just want to show here that, so I'm doing something 5,000 times and then doing it 50 times here. So in the beginning, when I'm deriving two samples, I grabbed two samples 5,000 times and then got the standard deviation of those two things and did that, got the standard deviation of the two things 5,000 times and then took the average of that. And that's less than the standard, that less than the one. Okay. But as my number of samples goes up from 2 to 50, I start approaching the one. So that's what I wanted to show here, that when on the sort of average, when I have a few samples, their standard deviation is sort of lower than the expected. And so we'll see here that the standard deviation of the two samples is lower than the one and approaches the one sort of when we're getting into the ballpark of 30, 40, 50 and somewhere in here. Oops. Okay. So now what I want to do, let's take this out for a second. All right. So I'm going to go back to the extreme example of just two samples. I'm going to get from a normal distribution, I'm going to get two samples. I'm going to get the mean and the standard deviation of those two samples. And then I'm going to create this quantity. And this is a standard quantity that one works with in statistics, where you're taking the mean and then you're scaling it by the standard deviation. But the standard deviation is itself sort of scaled by the square root of the number of samples. And we played with that idea previously, that when we played with the z-scores, the standard deviation often got scaled by the square root of the number of samples. So that is sort of that idea, if you're questioning that, is worked on in that other video. But so we're taking this quantity, the mean divided by the standard deviation, but divided by, and then that standard deviation is itself scaled by the square root of the number of samples. And we are doing that. Now, if this were not the standard deviation of the in samples, but the standard deviation of the original distribution, then this might be normal. And this might to you look normal, but will show that it is not. So let's take that data and make a histogram and remind you that here was the data. My list was the data of which I'm making the histogram. This second argument here in the histogram method is the B spec, the bin specification. And so I'm saying I want my bins to go from -6 to 6 and go up by eighths. And then I am saying, and I want the histogram to be a PDF probability density function or probability distribution function version of a histogram. So a normal histogram goes by frequencies, but I'm scaling it down to more probabilities, but I also am scaling it sort of in the horizontal direction, such that if I change my number of bins, it will still have overall the same height. So, and because this is the form that's good for comparing with math. Okay, the PDF. So here's the standard normal distribution that was the source of all of this. And let's compare it to that. So there is the normal distribution, standard normal, and let's put those two things together. So this was uh, my distribution. This is the standard normal distribution. We can see that they don't look alike. Now you could just say simply, coming up here to my, how does the standard deviation? Well, the standard deviation of here was low. Now, in this quantity, I'm dividing by the standard deviation. So this might end up to be, instead of too low, I might have things that are too big or something like that. But it's worse than that. So I can sort of calculate my standard deviation for my for the distribution, and I'm getting something like quite large. So if you thought that this yellow thing was a normal distribution, and I've just got, I mean, I've got the average right, it's around zero, but the only other parameter of this normal distribution is the standard deviation. So if you thought, well, I've just got the standard deviation wrong, let me fix it, and then I look at what my actual standard deviation is, it's gargantuan. So it's not even like on going from -6 to 6, and the standard deviation is 166. So if I made a normal distribution with that kind of standard deviation, there's no way that it would look anything like the data. It looks more like the data the way it is. So that's not the fix. Just a different normal distribution with a slightly different standard deviation is not going to fix it. It's because these tails are quite different. The normal distribution comes down quite rapidly, and this histogram with this sort of yellow histogram is not coming down. It has much, as I'll say, fatter tails. Okay, and this is where the what's called the student t distribution comes in. So this yellow thing, I'm not going to derive it or anything like that, but I'm just going to take my simulations and compare them to the student t distribution and see that it does capture that shape much better than the normal does. Okay, so the student t distribution has a parameter called its degrees of freedom, and it's compared to what we were just talking about. It's one less than the number of samples. So if I had two samples that I was drawing from the standard normal distribution to get myself started, then the corresponding student t distribution would have a degree of freedom of 1. And I'm just here sort of showing you, these are mathematical functions that and mathematical functions that Mathematica knows. And so that was 1 degree of freedom, 2 degree of freedom. Oops, what did I do here? 3 degree of freedom. And we see that the the normal distribution went like exponential of minus x squared, fell off quite quickly. These are falling off very slowly. They have very large tails. This goes like x the minus, x to the 2 in the denominator. This is sort of like x to the 3 in the denominator, x to the 4 in the denominator. So much longer, fatter tails, this t distribution. And again, we are sort of dividing by a square root, and the square root of the sample tends to be smaller. So this is part of its effect. Okay. All right. So now I'm making 2 mathematical functions here. the student t distribution with the number of samples minus one, because that it's parameterized by the degrees of freedom. And then again, I'm repeating my normal distribution. So I'm just plotting two mathematical functions here. The red is the student, the blue is the normal. And then I'm going to take those two mathematical functions and my data. And we see here that the red, the student with the appropriate degree of freedom, is very much closer to this histogram than was the blue, than was the normal. Okay. And again, this whole thing is about this confidence intervals up here. And this number, this 1.96, was based on a normal distribution. And if we want to replace the population standard deviation with the sample standard deviation, then we should move over to this student t distribution, which has, and then our z value is going to be quite different. Okay. So here we are. So now, what am I doing? This is, a lot of this is overkill. And so let's look in the middle and then move around it. So I'm getting a random mu and a random sigma. So mu is going to be a population, going to have a, a random number chosen to be the mean and a random number chosen to be the standard deviation of a normal distribution. And then I am getting, in this case, sample number was 3. I'm getting 3 samples from that distribution. So each time I change the distribution. I don't have to do that, but I just want to convince you that it's not sort of rigged up with some special value. So I'm grabbing values randomly and I'm changing them every time. From the normal distribution, I'm grabbing 3 samples. I'm getting the mean of those samples. I'm getting the standard deviation of those samples. I'm appending some stuff that I don't end up not using. But here's the part, here's the confidence interval part. Okay. So you remember that mu is the sample that mu is the actual mean of the distribution. And sigma was the standard deviation. But sample av was the average of my 3 samples, and sample standard deviation is the standard deviation of my 3 samples. And now I want to do this confidence interval. So I want to ask the question, is mu the population? Is it outside of the range? If that's greater than the sample average plus the sample standard deviation times some confidence number, I'm going to use the 1.96 and show that it's wrong. And then there's my square root of the number of samples. So again, that is this idea, except now the S is going to be from the sample. So I have the plus and the minus. So if my population mean, which I know in this case is mu, if it's above outside the range, I'm not going to count it. And then otherwise, I'm going to ask the other situation, is it less than, is it too low on the other side of the interval? And then I'm not going to count it. Otherwise, 1, I'm going to count it. So within is going to be a 1 if my population mean is within my confidence interval, and then I'm going to add it. And I have this data point and there's a result, and I'm not doing anything with it. I was doing more at another time. But the main thing is this am in. And am in, I have overall 1,000. I am looking to understand. I wanted 95% confidence. I'm using the old number, the 196, for 95% confidence. And so this number should be about 95% of 1,000, should be about 950. And we'll see that I'm not getting anywhere near that. You know, it's down in the ballpark of 800 rather than 950. It fluctuates a bit, but it's not fluctuating that much. It's not going to get up to the 950. Okay, so again, this 196 was based on a normal distribution, and we saw that it's not well described by a normal distribution. Uh, the blue is the normal, and it doesn't look like that. It looks like a student. So now we'll move over to student. And so we don't want the 196. We want our confidence, we want our Z value to be modified by the student T distribution. And then I'll show you what I did wrong and then do it right. Okay. So then I came over to this table from the student T table, and I said 3, which is wrong. And I wanted 95%, or, I'm allowing for 5% error or something like that. And so I said 3.182. So then I came in here and replaced my 196. And this is wrong. This is the 196 was wrong. This is also wrong. And then we'll fix it. But there's 910. No, that's not too far from the 950. But it's not, as I hover around it, I'm not getting 950. I'm pretty consistently below 950. And that's because the degrees of freedom and the sample number are not the same. So my sample number was 3, but my degrees of freedom is supposed to be 2. And so I'm going to call it the Z value. I don't quite know what to call it, but I'll also call it Z, should be 4303. And I just changed it in the wrong place. This is the right place to change it. I'm jumping all over the place. Here's the right place to change it, 4.303. And now I should be getting in the ballpark of 950s. So if my number of samples is small, then I want the confidence interval based on this small sample, then I should grab this Z number to construct my confidence interval from a T table, a student T table, and not from the normal distribution. Okay. And then so the standard number is 196. So if you had an infinite number of samples, then you're getting to the 196. If you had 1,000 samples, you're close enough to the 196. But some people will talk about 30, some people will talk about 50. It depends how worried you are about tails. But that is the idea. That's what I wanted to show. Okay. So there is this idea of the confidence interval of we have some data from a sample, and we want to say with how much confidence we think we can put a bounds on the quantities for the whole population. And if we knew this idea of the Z was based on the sample standard deviation, the population standard deviation, But if we want to take the same idea and move it over to the sample, we can do that, but the z has to be modified. The z can't be pulled from the normal distribution. The z must be pulled from the student t distribution, and then the z's end up to be larger. Now they are also, of course, dependent on the number of uh, how much confidence you want, but also on the number of degrees of freedom. So we chose only 3 samples. Our degrees of freedom was 2, so we were pretty high here. But it comes down, we can get it from 4.3 to like 2.2 by just having sort of 11 samples. So this number, we can shrink the interval. We're we're shrinking it sort of almost sort of in 2 ways, because there's already this sort of square root of the sample size sort of helping us shrink this, but it's also shrinking so that the sample size not only has this sort of square root of n dependence, but also is affecting the z here. So there's sort of 2 effects here. Okay, that's what I wanted to show, and I sort of gained some intuition with by playing with Mathematica. Thanks for your attention.